Okay there, let's go ahead and talk some ANOVA. ANOVA, also known as analysis of one-way variance. So this is really a test for multiple means. So when we have three or more groups or three or more samples of separate independent groups and we want to compare them, that's what the ANOVA testing is. Now there is a one-way and a two-way ANOVA testing. For this class, we're just going to do one way. And so this is right tail only. So this test is always a right-tailed test for us. So we're collecting data. It's a quantitative variable for every group. And then you have a couple categories or groups, right? If you think about it, you have your several groups, and then for those groups, they're going to have parameters. So as you can see here, like group 1 is going to have an average and a standard deviation. Group 2 will have an average and a standard deviation, etc., etc. And those are the populations. Those are parameters. But we don't know those, so what do? Well, we go out, we take a sample, and we get our sample mean, sample standard deviation, and the size of a sample for every group. So those are kind of the variables and the labels we're working with. So the question becomes, are these groups the same or different, right? And if so, which ones are different and how can we tell? And so that makes sense. You know, that's usually what our null says. Null says there is no difference. And that's what we're doing here. All right. Now, it's a right-tailed test. Why is that? Well, similar to goodness of fit and independence, if they're all roughly the same, then there's zero difference. And if there is a difference, the larger and the larger the number will get, or the larger difference. And so then we get a number further away from zero. And the further we are from zero, then we're going to reject. So that's why it's always a right-tailed test. For this one, though, we're going to use the F distribution, not the chi-square distribution. We're going to use the F distribution. And so let's just go ahead and go through the hypothesis test. So same 8 steps as all of our hypothesis tests. And in this case, the null always says they're all equal. So all the means for all the groups are equal. And so the easiest way to do that is just mu1 equals mu2 equals mu3 up to how many groups you have. And then remember, mathematically, logically, the opposite of all equals is at least one is different. Because if one of them is different, then that means that the null, them being all equal, is false, right? And so it is a logical opposite there. So at least one is different. So that's what your null and alternative will always look like. All right. In terms of conditions, of course, each sample must be randomly selected or normal. They must be independent. And then each population must have the same variance, or roughly the same variance. And that's an assumption that we're going to make on these problems. And so we're not going to worry so much about that. All right. So the test statistic is essentially, it takes the variance between the samples and divides it by the variance within the samples. All right. And so we'll explain what that is in a second, but the variance between, we signify that with this thing called the mean squares between. So MS sub B, the mean squares between. And then the variance within, we calculate that and we call that thing the mean squares within. All right. So our test statistic is really the mean squares between divided by the mean squares within. And we used, again, that F distribution. There's your degrees of freedom because, notice, this is a fraction, so it does have a denominator. And so therefore there's a degrees of freedom of the, I said that backwards. That's a numerator. So there's a degrees of freedom of the numerator, and then degrees of freedom of the denominator, right? And so that's the 2 degrees of freedom, one for the top, one for the bottom, right? So kind of similar to your two variance idea. All right. Again, there's your F distribution. Similar to chi-square, remember it's not symmetric, but it's always skew right. All right. So let's just do a quick visualization of how the formula works and what it really does. So here we go. This is a population, and from it we sampled 3 groups, and there we go. So the first step is you find what's called a grand mean. All right, and so it's kind of like you lump, or using words we used before, pooled everybody together into one large sample and find the mean. And so that's called the grand mean. So it's the mean of all of the samples put together. Notice that it's got 2 bars above the x, so x double bar is the grand mean. Then we find, of course, the statistics for each sample. So the mean and standard deviation of each sample. Pretty basic stuff. Statcrunch can certainly do that for us. And then now we start to calculate it. So before we get into the mean squares within and the mean squares between, we calculate what we call the sum of the squares. Now check this out. We call it the sum because we're summing, adding them up, of the squares. Notice what we're doing over here. We're squaring. So it's the sum of the squares. So for each group, we're going to do this. And if you notice, there's an n, that's the size of that group, that sample. This also comes from that group. Now this is the grand mean. So that's the betweenness part here. So the grand mean was when we looked at everybody all together, or it's the mean between all of them put together, if you want to think of it like that. So the sum of the squares, and because we're using the grand mean, it's between. All right, so that's the sum of the squares. And then you take that sum and divide by the degrees of freedom, because we're finding a mean, right? It's the mean squares, right? Mean squares. And so how do you find a mean? How do you find an average? Add them all up, divide by how many? Well, what did we do up top? We added them all up. It's the sum of the squares. So add them all up, divide by how many? The how many, though, is the degrees of freedom. And if you didn't catch that before, K is the number of categories, right? So there we go. That's the mean squares between. Now we do a similar thing. We do the sum of the squares. But now we'll say within. Why do we say within? Well, because this number is just from inside of that sample, and that number is from within inside that sample. So we'll calculate that for one sample, we'll calculate it for another, we'll calculate it for another, and we'll add them up. So the numbers for each piece are coming within the samples, so hence the idea of within. So that's the sum of the squares, and then just like before, we'll find the mean squares within. So you sum them all up, divide by how many. So this degrees of freedom is kind of like the how many down here. So add them up, divide by how many, and that gets you the mean squares within, right? Okay. And then you divide those, you'll get a number. It's always going to be positive because we've been squaring everything, so that makes things positive. And so we get a number greater than 0. The closer we are to 0, we will fail to reject. And then the further we get away from 0, the more and more likely it is we're going to reject, right? And so that's what I said here. All right. So, and then when you're done, what we do is we summarize all these parts in a table, and this is called an ANOVA table. And Statcrunch actually gives us an ANOVA table when we look at that. All right, so let's move on. Here's a real small sample. I'm going to show you all the parts as if we calculated it longhand and everything, but we won't have to do that longhand. We'll let Statcrunch do all the hard work, but I think it's just helpful just to see it all kind of go through the motions here. So here's 3 small samples. So first of all, the grand mean. So add them all up, divide by how many. So get 3.71426. Awesome. All right, now there's your statistics for every sample. No big deal. All right, so now let's do the sum of the squares within. Or actually, this is, between. So we're going to run this formula. So for the first formula, what's n for my first sample? Well, n is 4. What's x bar for my first sample? Well, x bar is 3. And then the grand mean, which is a little bit different, right? That's not from within the sample, that's kind of outside of it, but there it is. So we did that for sample 1, then we'll do it again for sample 2, do it again for sample 3, add them all up. So there you go. So there's your sum of your squares between, right? And so we get 2.857. Here's your sum of your squares within. So let's jump back here. And so n, well, what's n? N is this. What's the standard deviation? Well, there's my standard deviation. So there it is, and then we square it. And there's my n. And so these values are coming within that sample. Then we do the same thing for sample 2, same thing for sample 3. Sum them. We got 34. So there's my sum of my squares within. And then divide, right? So the mean squares between, we divide by the degrees of freedom. Mean squares within, divide by the degrees of freedom. And then we get the two different mean squares values, and then we divide those, and we get our test statistic. All right, and you can do this in Statcrunch. So you type the data in columns, then you go to Stat ANOVA one way. So we'll demonstrate this in a little bit in Statcrunch. But you do that, and then it'll spit out the data, and this is what it looks like in Statcrunch. So down here is that ANOVA table, and then also you can see the statistics up here. So you have your mean, your standard deviation, and for all your groups. So you have all your nice statistics up there as well. So that's nice. Okay, so really for your work, what I'm going to ask you is Statcrunch does all the hard work. So I just like to see the sample statistics, kind of write those out. I'd like the ANOVA table, and then just draw the distribution and shade. Of course, p-value and decision. So let's just model that in one example real quick. So we got a medical researcher wants to determine whether there is a difference in the mean length of time it takes 3 types of pain relievers to provide relief from headache pain. Several headache sufferers are randomly selected and given one of 3 medications. Each headache sufferer records the time in minutes it takes the medication to begin working. The results are shown on the next slide. At alpha equals 0.1, can you conclude that the mean times are different? All right, so remember the null says they're all equal, so different would fall within the alternative. So this time your claim would be in the alternative hypothesis. And then it makes a statement about the assumptions at the end, so that takes care of our conditions. So, all right, so alpha of 0.1. Okay, so there we go. There's our data. We can put it in Statcrunch. There is your mean or null hypothesis, alternative, and like I mentioned, it said test to see if they're different. That would be in the claim then. So alpha was 0.1. Degrees of freedom, the numerator, that is, I believe, k minus 1. And so k minus 1, how many categories? We have 3 categories or 3 groups, so my degrees of freedom of my numerator is 2. This is capital N minus K. Yeah, no, that's right. So let's see here. Looks like we have 1, 2, 3, 4, 12, 13 pieces of data. So capital N in this case is 13. So this is a special case where N is not the population size, it's the total of all the samples. And K was 3, so degrees of freedom of the denominator is 10. My distribution, by the way, that's going to be an F distribution, right? And so then we can get our ANOVA table. Before we do that, though, I do want to draw my distribution out. And so let's go ahead and go into Statcrunch and let's get our critical value. So F distribution, degrees of freedom 2, 10, and an alpha of 1. So I do have Statcrunch here. So I'm going to go Stat, Calculators, F. Alright, so degrees of freedom was 2 and 10. This is always right tail, so I need to switch that and put in my alpha value, which was, we had a small alpha value, 0.1. Compute. So actually it's off the chart. My critical value is 7.5, we'll just say 7.56. How about that? So we'll go back and you notice it looks something like this. And so I have a critical value out here of 7.56. So if I land out there, I'll reject, and just as a reminder, that was 0.1 big. Okay, that's it. So then I can let Statcrunch do all the hard work. So let's get our ANOVA table. So let's go back to Statcrunch. I'm going to close that out. So I started typing the data in just to save some time, but let's finish it off. So it was 17, 20, and 15. Alright, so I can just go to Stat, ANOVA, one way. We're always doing one way in this class. Alright, select your items. There we go. So I selected my 3 columns, and that's all I have to tell it for our purposes. It'll do a whole bunch of other stuff, but that's all we need to do. Just select your columns. And there you go. There's your ANOVA table. So you can see the ANOVA table down below here, and has all our nice, lovely results. And so if I go back into here, on the exam, I'll actually give you a blank table to fill in, so you just need to fill in the table. So this would be what? This would be 2, this would be 10. By the way, Statcrunch calls it columns and error, but really that's between and within. And then we'll just copy the other parts. So this is 21.92. Alright, and then how do you get the mean squares between? Well, you take the sum of the squares divided by the degrees of freedom. So if you took 21.92 divided by 2, you would get the mean squares value. So 10.96. But it's right there in the table, so if you're just copying right out of the table. We got 73 here, and 7.3, which makes sense because 73 divided by 10 gives me the mean squares. And then now if I take these two and divide them, that would give me my test statistic. So 1.502, and my p-value is 0.02. Oh no, reading that wrong. It's 0.269. Okay, so I had this pulled up on another screen. I was reading it off that screen, but all I'm doing is I'm just literally copying these values right off of this ANOVA table here. Okay, so that's all I was doing. Cool. And so compare what? Compare your P to alpha. That is definitely greater than alpha, which was 0.1. So what are we going to do? We are going to what? Fail to reject the null. So therefore what? Well, remember the claim was in the alternative, saying they're different, but we're gonna fail to support that claim that they're different, because we failed to reject the null, which says they're all equal. So there you go. All right, So there's another example in the notes. I'm not going to run through that, but you can again type all these in the columns, have it spit out the ANOVA table, and you're good to go. So Statcrunch does almost all the work on this one. There isn't a whole lot to do. The setup's fairly easy and all that. So if you need another example, though, I believe there is another example in Blackboard that's worked out different than these. And otherwise, that's ANOVA.